Hi everybody, this is Homer White back again with part 4 of the 8th chapter of our course. This chapter is on probability in sampling. And in this part we're going to turn things around. Instead of studying probability, where we imagine ourselves as godlike beings who know what the population is and who are wondering what are the chances for estimators to turn out to be various things, we're going to turn it around and realize that we're just mortal people who take samples from populations, and we'd like to be able to make estimates of the parameters within them. We'll also learn about the 68-95 rule for estimation. Always remember to make sure that the necessary packages are loaded. So, let's go from God back to mortal. So in reality, you are not a godlike being, as we've been considering in our examples from probability in the last video lecture. You're just a mere mortal, a statistician, and you've taken a simple random sample of size, let us say n, from some population. So the following things are all true about you. You don't know the population mean, mu. You don't know the population standard deviation, sigma. However, you've taken the sample, and you can compute from the sample various statistics. In particular, you can compute the sample mean x bar. So you do know what x bar is. You also know that before you took the sample, x bar was liable to turn out to be within a standard deviation or so of its expected value, mu. That's because you know basic probability theory. So you figure that for the sample that you have just taken, x bar is a standard deviation or so away from mu. In other words, the population mean mu is liable to be within a standard deviation or so of your sample mean x bar. The only problem is that the standard deviation of x bar is the standard deviation of the population, sigma, divided by the square root of the sample size. You know your sample size n. After all, you took the sample. But you do not know the population standard deviation, sigma. So you don't know the value of this thing that you think is the likely difference between your x bar and the mu that you're trying to estimate. There is a solution, though, a partial solution to this problem. You can estimate that unknown population standard deviation, sigma, with s, the standard deviation of your sample. This leads you to an estimation of the standard deviation of x bar, and this estimate is called the standard error of x bar. So the standard error of x bar is s divided by the square root of n, the standard deviation of your sample divided by the square root of n. We can use that figure as an estimate for the standard deviation of x bar. For example, say you take a sample of size 36 from a population with some unknown mean mu. From your sample, you compute that x bar is 60, let's say. And also, let's say that from your sample, you compute that the sample standard deviation is 3. Then you can estimate the standard deviation of x bar by the standard error of x bar. That will be 3 divided by the square root of 36. This works out to exactly 1/2. So you figure that mu is liable to be within 1/2 or so of 60, which was your sample mean. So you have a ballpark interval for mu. But there's more. Your sample size, 36, was big enough beyond our cutoff where we typically say that the central limit theorem kicks in. And so by your probability theory, you know that x bar as a random variable was about normal. Since there was about a 68% chance that x bar would be within one standard deviation of mu, remember that's what the 68-95 rule for random variables said, then you can go on a limb a bit and say, I'm about 68% confident that mu is within one standard error of my x bar. In other words, you could say, I'm about 68% confident that mu is somewhere in between 59.5 and 60.5. You've just taken away a standard error and added a standard error to your x bar figure. Now you are going a little bit out on a limb here, After all, the probability theory said there was a 68% chance that x bar would be within one standard deviation of mu. And here you are saying you're 68% confident that mu is within one standard error of x bar. Really, you should be saying you're about 68% confident that mu is within one standard deviation of x bar. So there's a little bit more approximation going on here. You're a little bit more out on a limb. In general, there's a 68-95 rule for estimation. It's a new version of the 68-95 rule. This is the third version of the rule that we'll learn. Here's the rule. If the probability distribution of an estimator is approximately normal, then we can be about 68% confident that the parameter that we're trying to estimate will be within one standard error of the estimator. We can be about 95% confident that the parameter will be within two standard errors of the estimator. And we can be about 99.7% confident that the parameter will be within three standard errors of the estimator. Notice we use the word confidence here, and we don't use the word chance. That's because we've already taken the sample. We already have our estimator. It's x bar maybe. It's a particular number now. And the standard error, that's computed from our sample. That's a particular number. So when we go one standard error in either direction away from our x bar, let us say, then we're going in some definite interval. That interval either does or does not contain the parameter we're trying to estimate. There's really no chances about it. But because the sample was taken in a situation where probability theory said that before it's taken, there was about a 68% chance that it would come out to within one standard deviation of the population mean mu, then after the sample is taken and all the chances are gone, we can be 68% confident of being within one standard error of the population mean. So let's go back to the previous example and jazz things up a little bit. So you've taken a sample of size 36 from a population with an unknown mean mu, and from your sample you compute x bar is 60. From your sample you further compute that the standard deviation of that sample is 3, and then just as before you compute the standard error of x bar, and it's 0.5. Let's make some of these intervals. If we add and subtract one standard error to the x bar, then we get a rough 68% confidence interval for the population mean mu. We're about 68% confident that mu is bigger on the one hand than x bar minus a standard error, and less, on the other hand, than x bar plus a standard error. So we're 68% confident that mu lies somewhere in between 59.5 and 60.5. That interval of real numbers from 59.5 to 60.5 is called a 68% confidence interval for mu. Remember, it's just a rough 68% confidence interval. After all, the 68% figure came from the 68-95 rule, which is assuming that x bar has roughly a bell-shaped distribution as a random variable. And we've also substituted standard errors for standard deviations, and that roughs things up a bit more. You can make a rough 95% confidence interval for the population mean mu. You can say that you're about 95% confident that mu is bigger than x bar minus 2 standard errors and less than x bar plus 2 standard errors. Now 2 standard errors is 2 halves, that's 1. And so you're 95% confident that mu is somewhere in between 59 and 61. If you'd like to be even more confident about where mu is, you'll have to make a wider interval. You could say that you're about 99.7% confident that mu is somewhere in between x bar minus 3 standard errors and x bar plus 3 standard errors. 3 halves is 1.5, and so you're 99.7% confident, roughly, that mu is in between 58.5 and 61.5. Now we've been talking in terms of estimating a population mean mu using the standard estimator x bar. There are 4 other basic 5 parameters, each estimated with their own estimator. And the neat thing is that the standard deviations for each one of those estimators can be estimated with standard errors in exactly the same way. Just plug in basic estimates for population parameters wherever they show up in the formula for the standard deviation. For example, in the difference of sample means, here is your formula for the standard deviation of x1 bar minus x2 bar. It has a couple of population parameters in it. It has sigma 1, the standard deviation of population number 1, and sigma 2, the standard deviation of population number 2. So if you simply replace those standard deviations with the standard deviations of the samples that you've taken, those are numbers you can compute, then you have the standard error for x1 bar minus x2 bar. And you can construct confidence intervals, rough 68, 95, and 99.7% confidence intervals for mu1 minus mu2 using this standard error. The same can be done for p hat, for p1 hat minus p2 hat, and for d bar. Just replace parameters with their natural estimators. There's a lot more to say about confidence intervals. In the next chapter, we're going to learn how to make more of them, and we're also going to learn how to make them less rough. Thank you for listening.